The PageRank of a website gives the relative importance of the website. In this video we will discuss a mathematical model for the web server. This model allows us to compute the PageRank of every website. The assumptions behind the model that we will develop are as follows. To go from page to page, the web server is allowed to follow hyperlinks, or to go to a page by typing in the address of a page in the toolbar. This latter action is called teleportation. Using these two actions, so following a link or teleportation, we can derive a model for the probability that the web server is on a website. The PageRank of a website is the probability that the web server ends up on that page after randomly surfing the World Wide Web for an infinite long time. As a first step towards a mathematical model, we first consider the World Wide Web as a graph. The figure gives a very simple example. The circles with the numbers represent the web pages, which are the nodes of the graph. The arrows between the circles are hyperlinks. An outlink is a hyperlink from a website to another website. So if you are on a website, you will leave it by clicking on an outlink. Many pages do not have outlinks. Think for example of images. If you end up on such a page, you cannot leave it by clicking on a link. Such a website is called a dangling node. Now the graph can also be represented as a binary matrix, that is a matrix with zeros and ones. And we call this matrix the matrix G. A column of G represents a node or a website. Let's call this node J. Then the jth column contains on position I a 1 if node J has an outlink to node I. In the graph, node 3 has outlinks to nodes 2, 4 and 5. This means that column 3 of J has 1s in positions 2, 4 and 5. Note that columns 6 and 7 only contain zeros. That is because nodes 6 and 7 are dangling nodes. Now let's look again at our matrix G. This matrix only gives connections between pages. The next step is to make, using the matrix G, a probability matrix, PT, P transpose, that specifies the chance given that we are on a certain website, to end up on another website. To be more specific, assume that we are on website 3. What is the probability of ending up on one of the other websites after clicking one time? To compute this chance, we assume that the server follows outlinks with equal probability. So, looking at node 3 again, after one click there is a 1 over 3 chance of ending up on either page 2, page 4 or page 5. Note that probabilities are always non-negative, and the sum of the probabilities is 1. The dangling nodes are a special case, since we cannot click on a hyperlink to leave them. That means that we always teleport from dangling nodes. We jump away. Every page has an equal chance to be the destination. The probability is equal to 1 over the number of websites, because every website has the same chance to be the destination website. So we can now put all these probabilities in a matrix PT, as shown here. Going from G to PT is simply done by dividing the columns of G by the number of non-zero elements in the column. 0 columns in G for the dangling nodes become constant columns in PT with the constant equal to 1 over the number of the website. This matrix PT is a so-called stochastic matrix. All entries ij of the matrix represent a probability or a chance and are therefore non-zeros between 0 and 1. These numbers represent the chance that you serve from website J to website I. The columns of PT add up to 1. This simply means that the server will end up somewhere on the web with probability 1 after clicking. Now let's look at the given probability distribution. So every page has a certain chance that the server is on it. The initial probability distribution vector, called x0, contains these probabilities. So the numbers in x0 are between 0 and 1. And the sum of the values in x0 is 1. So the total, all the probabilities, they add up to 1. And this is since for sure the probability that the server is on since for sure the probability that the server is on meaning any page in the website, is 1. So you're always somewhere. Now we do one serving step, one iteration. What is after one step the probability that the server is on a certain page? This probability can simply be calculated by multiplying our initial distribution x0 by the probability matrix PT that specifies the chances of going from one website to another. So if x0 is our initial probability distribution, x1 is given by PT times x0. Now note that x1 also has values between 0 and 1, and the numbers add up to 1. So x1 is again a probability distribution. We have modeled the probabilities if we follow outlinks, plus a teleportation fix for the dangling nodes. But this does not model the complete behavior that also includes teleportation. Teleportation away from a page to another page. Simply because we decide not to follow a link, but to put the web address in the toolbar. To model the probability of this behavior, we assume that the chance that we follow a link is P and the chance that we teleport away is 1 minus P. Furthermore, we assume that every page has equal probability to be teleported to. So every page has the same probability of being the destination page. The value P is sometimes called the PageRank damping factor. It is usually taken to be 0.85. So there is a chance of 0.85 of following an outlink and of 0.15 of teleportation. The teleportation behavior can be modeled by a probability matrix with probability 1 over n for, and n is the number of websites, for all transitions from one page to another page. So by teleportation you can reach any page from any page with equal probability. The final Google matrix A, we will call it A, is now given by the probability P that you follow a link times the probability matrix PT plus the teleportation probability 1 minus P times the teleportation probability matrix. The resulting matrix A is again a stochastic matrix. All entries are between 0 and 1 and columns add up to 1 again. Given an initial probability distribution vector x0, we can compute the probabilities for being on a certain website after n transitions and steps by multiplying this initial distribution n times with the Google matrix A. So doing this infinitely many times should give us for each page the chance that we are on that page after infinitely long surfing. And this was what we called the PageRank. Now this algorithm is clear, but it leaves us some questions. First of all, does this converge to a stationary vector? So do we get a fixed value after infinitely many steps? Or do the distributions keep changing? Secondly, if it converges to a stationary vector, Does this vector depend on the initial distribution? So do we get for every starting vector a different result, or is it always the same? The last question is this calculation actually feasible? Meaning doable in a reasonable amount of time? The problem is, of course, that there are billions of web pages. So the matrix A is really tremendously big. It is huge. Now these questions, they will be discussed in the third video.